as we have previously observed, the VIM explicitly defines the measurement result as the set of quantity values being attributed to a measure together with any other relevant and available information. This definition takes into account the fact that, since we cannot know the true value of the measurement result only provides us with an approximation of it. There therefore exists an uncertainty regarding the accuracy of the result, that is, a doubt as to how well it represents the value of the measured quantity. The other information mentioned by the VIM is precisely intended to assess the measurement uncertainty, that is, the quality of the approximation with which the measurement result allows us to know the value of the measurand. The first step to take in order to assess it is to identify the sources of uncertainty, that is, the causes of doubt regarding the correctness of the result. To do this, it is useful to refer to the measurement model we analyzed previously. Let us begin with the identification and definition of goals, conditions, and the mathematical description of the measurement context. Even at this initial stage, some approximations are inevitably made. Let's look at a simple example. We want to measure the width of a table, for instance, this one. In order to achieve this, we simply take a measuring tape, place it along the side to be measured, with one end on the edge, and then carefully read off the width measurement at the other end. Why do we proceed in this way? Because unconsciously we refer to a rectangular geometric model of the tabletop. But is it really like that? In reality, it is only an approximation that depends on the quality of the manufacturing process. It is not the only possible approximation. The effects of certain influence quantities may be neglected or described by an approximate relationship. For example, the relationship between temperature and expansion, which we saw in a previous example, is often considered linear, but such an approximation is only valid for temperature variations of a few tenths of degrees centigrade. All this contributes to what the VIM calls definitional uncertainty, defined as component of measurement uncertainty resulting from the finite amount of detail in the definition of a measurand. To put it another way, not knowing all specific details of the measurand, in simple terms, not knowing exactly what is being measured, inevitably results in a sense of doubt about the degree to which any measurement result truly represents it. The VIM notes that definitional uncertainty is the practical minimum measurement uncertainty, achievable in one measurement of a given measurand. On a closer look, it is an obvious consideration. If we do not know exactly what to measure, we cannot improve our knowledge through the measurement itself. In other words, it is pointless to use high-quality instruments to measure a quantity that we cannot define properly. A component of definitional uncertainty also arises from the approximations used to describe the interactions between the measurand, the environment, and the measurement system. The other part of the measurement model that gives rise to a significant contribution of uncertainty is that of the experimental processes in which measurement systems are used. Here arises the component known as instrumental measurement uncertainty, defined by the VIM as a component of measurement uncertainty arising from a measuring instrument or measuring system in use, where the measurement system refers to the set of instruments and equipment, including the operator, necessary to carry out the measurement. This component of uncertainty is often mistakenly considered the only or the most important component of uncertainty. Let's see what it depends on. We know that the instruments used are not ideal. The values they produce may differ from the value of the measurand. If you repeat the measurement of the same measurand, they may give different values both in the short term due to disturbances and in the long term due to drift. Let's consider, for example, a scale. If we weigh the same object several times, we may obtain different values because of vibrations, the position of the object on the plate, or drafts. If we repeat the measurement after some time, we may get different values again due to drifts in the scale caused by changes over time in its internal characteristics. We will see in the next videos that instrumental uncertainty can be assessed by means of an operation called calibration. Without going into the details which we will look at later, calibration requires measuring a reference quantity whose value and uncertainty are known. The latter, therefore, represents the lower limit of instrumental uncertainty. Therefore, the choice of references to be used in calibration is an important aspect of measurement activities, as it has a direct impact on instrumental uncertainty. Another important point concerns the operator. The operator is the person who carries out the measurement from the initial stages of setting up the measurement system to the reading and processing of the measured values. The operator is therefore an integral part of the measurement system and may unconsciously make small errors that affect the measurement result. So the operator also contributes to instrumental uncertainty, and it is necessary to assess his or her contribution. To sum up, the measurement model makes it possible to identify the stages from which the overall uncertainty originates. We have identified two main contributions: the definitional uncertainty and the instrumental measurement uncertainty. Both are always present, and their relative importance varies depending on the type of measurement. In some cases, instrumental uncertainty prevails, while in others, definitional uncertainty is more significant. It is therefore essential to carefully assess both in order to ensure the reliability of the measurement result.